We finish our discussion of the flow around the ideal flow around a cylinder by looking at the stagnation points which can be found in the flow. Okay, so let me go back to the flow that we derived. Remember that this is the velocity field, which is the flow around a cylinder. All right, so recall again so we're looking at the stagnation points. Recall our velocity field. That is our velocity field around the cylinder. Of course, we are interested at what happens to the velocity field when we are at the surface of the cylinder. So this is when r equals to a. Of course, at r equals to a, the radial component is equal to 0 because that's the no penetration boundary condition that we imposed. So at r equals to a, this is equal to 0. And our only non-zero component is in the circumferential direction, and you see that it's equal to minus 2u sine theta plus gamma divided by 2 pi times a. Okay, so this is our velocity at the surface of the cylinder, and now if we are looking at the stagnation point, we are looking for points such that the velocity is equal to 0. Right, or the norm of the velocity is equal to 0, and so stagnation point at the surface of the cylinder will be points for which the theta, not only the normal component, but also the circumferential or the circumferential component of the velocity or the tangential component to the surface, when this is equal to 0. So the equation which characterizes the stagnation point is we need that this component is equal to 0, and therefore we need that 2u sine theta is equal to gamma divided by 2 pi a, which here I'm simply going to write for an equation for gamma. So we need that the circulation gamma is equal to 4 pi a u sine theta. Or actually, no, let me write it more for as an equation for theta, right? Because this is only going to be true at certain values for theta. So we need that sine theta be equal to gamma divided by 4 pi a u. No, actually, I changed my mind again. I'm going to write it in terms of gamma. So our equation that needs to be satisfied is that gamma is equal to 4 pi a u times sine of theta. Okay, so what can we infer from that? So let's see. Let's assume that we take this function here. Right, we're going to plot the function 4 pi a u sine theta. So this is a sine function. It looks like this. So 0 at 0. It becomes 0 again at theta equals to pi. And then between pi and minus 2 pi, and 2 pi, sorry, it becomes like that. And the maximum value here is 4 pi au. And we'll start with gamma equals to 0. Okay, so if gamma equals to 0, that corresponds to here. Right, so this here is gamma equals to 0. When is this function equal to 0? Well, we see that it's equal to 0 at 0, pi, and 0. And so this here, our stagnation points are located at 0, pi, and 2 pi, and we've seen that before. If there is no circulation, right, the flow looks like this, and your stagnation points are for here when theta is equal to 0, and here when theta is equal to pi. So this is what we have. Now let's say that we take a small non-zero gamma, and we want positive lift, so we're going to take a slightly negative value for gamma. So let me take a value here for gamma. In that case, gamma is slightly negative. It's not too big. And what do we find? We find that we have two stagnation points, which are going to be here for theta slightly larger than pi, and for theta slightly smaller than 2 pi. Right? So where are these stagnation points? So remember, now we still have a cylinder, but now we added a slight negative circulation, and if you remember from the images, the streamline started to look like this, right? And indeed, you find here that you have one stagnation point at a value slightly larger than pi, right? So I have one stagnation point, this is 0, this is pi, and you see that I have one stagnation point here, which is for an angle theta, which is slightly larger than pi, and another stagnation point here, which is for a value of theta, which is slightly smaller than 2 pi, yeah? And then there will be a limiting case when the circulation becomes even larger. That will correspond to this case. So when you're right here, when gamma is exactly equal to 4 pi AU, then this is my cylinder. Now I'm adding a lot of circulation, right? And this is when the two stagnation points come together and just come at the bottom of the cylinder for an angle 3 pi divided by 2. Right? So that here corresponds to gamma equal to absolute value of gamma. So gamma here is equal to minus 4 pi AU. And if you take a value for gamma which is even lower than that, lower because it's negative, so a even bigger negative value for gamma, then you see that you no longer have any stagnation points at the surface of the cylinder, and that corresponds to what we had. Remember when we had a very, very big negative value for the circulation, then there was almost a pocket of recirculation here with closed streamlines. And we had a stagnation point, which was no longer at the surface of the cylinder, but which was in the bulk of the fluid. And so you had something which looked like that. All right, and so this is how the stagnation points look like for the flow around a cylinder.